Okay, so now I'm going to deal with a slightly more awkward situation. And we're back to the algebraic eigenvalue problem here. A and B are these matrices. We're calculating the solution for x and lambda. All right, now the example that we had before, it had repeated eigenvalues. And this is the issue. What do you do when you have repeated eigenvalues? Because it's not quite so straightforward, as we shall see. There are two possibilities, non-degenerate and we just have multiple eigenvalues, but we have the right number of eigenvectors, and then there's the degenerate case when we have an insufficient number of eigenvectors to proceed. And you have to treat the situations differently. So the second segment, I'm going to deal with this case. All right? So that's the plan. Right. So given that, let's now think of an example where we face some of these issues. So let's do the following one. A will be 1, 0, 2, 0, 1, 0, and 0, 0, 3. So, as the lecturer, I have the luxury of using triangular matrices so I can read off my eigenvectors and eigenvalues, and the eigenvector calculation is straightforward. Of course, under test conditions, you don't have that luxury. And it gets bad depending on how sadistic the instructor is. Okay, so there's my A, there's my B. Now, the quick calculation is just to choose 3 there. So if I choose A is equal to 3, then you can easily confirm that the eigenvector is 1, 0, 1. If I take that and multiply it, you'll see that it works. And the corresponding row eigenvector is 0, 0, 1 again. Actually, it's very similar to the problem that we did to begin with. Okay, right, so given that, I had this formula before, which was lambda 1 is equal to minus E dagger BE over E dagger E. That was the formula, so we can simply plug in. We can do all of the calculations for the numerator and the denominator, and you find that lambda 1 is minus 2 again. That's just going through the exercise that we went through before. So that's the easy case. That's because that particular eigenvalue has got a multiplicity of 1. But what about the other case? So in the other case, if I choose A is equal to 1, then I have to solve the following problem to get the eigenvector. So A minus AI times the eigenvector has to be 0, 0, 0. That's the computation for the eigenvector. And if I just subtract 1 from the diagonal, I get 0, 0, 2, 0, 0, 0, and 0, 0, 3 times E is equal to 0, 0, 0. All right, so that's what I have to solve to get the eigenvector. And 2 of these equations just tell me that the third component has to vanish. The middle equation doesn't tell me anything, so the first 2 components of the vector here could be anything. So I can pick E to be either 1, 0, 0 or 0, 1, 0. They both work. And they're orthogonal. Clearly they're orthogonal. So for this particular repeated eigenvalue, there are 2 possible independent eigenvectors. All right, so that's the good case. That's the non-degenerate case where you have a multiplicity in the eigenvalue, but you've got the right number of eigenvectors to make up the whole thing. Right? So there's an eigenvector here that corresponds to that one, and then there are these 2 that correspond to this. So there are 3 independent eigenvectors. That's the good situation. Okay, well, corresponding to this eigenvector, there's a row eigenvector, and you can do a quick calculation and verify that I can choose either 1, 0, minus 1, or 0, 1, 0. right? Both of these work. If I just go through and verify it. Okay. So what does that mean? Well, that means, well, I could just pick one, right? So I can try A and E equals 1, and let's pick the first one. I can pick this pair. What is lambda 1? Well, I can use the formula that we've already derived. I can just plug in everything and calculate a lambda 1. And you will get an answer by doing that. However, the problem is that when we were building the whole theory here, at some point we arrived at this equation. This is the equation for x1. And we've picked an A, we've picked an E, and we need to solve this for both the x1 and the lambda 1. Now, the way that we did that is we applied the Fredholm alternative by multiplying by the row eigenvector. You take your row eigenvector, that one for example, you multiply this equation by, gets rid of the left-hand side, you get this formula for lambda 1. However, I have two options. I can multiply by this one, or I can multiply by that one. Right? I can pick this one and A is 1, or I can pick that one and that one. Right? So I can choose a pair and then try to compute the correction, but I've got two possibilities for the killing eigenvector that gets rid of the left-hand side to generate a different lambda 1. And you can see what the issue is. So I'm going to have picked an E, but I've got two possibilities for these. They're clearly going to give two different values for the lambda 1. So which value of lambda 1 I get depends on whether I choose that one or that one. So there's something that has gone wrong here. We've got some ambiguity in what we've done. So let's go back to the drawing board a little bit and see what we can do. Okay, so I'm going to quickly go through the erasure of this. Let's keep that information now. I guess I don't really need this bit at the top now. I need this information now. Okay. Right. So what I need to do is I need to step back a second and revise what I'm thinking about doing here. And I need to do it in such a way that I give myself the freedom to avoid any ambiguity. It's a question of remaining general to avoid any pitfalls. So when I went through, what we said was that, well, okay, then the leading order solution corresponded to one of these pairs, right? The eigenvalue was 1, and then I had an eigenvector. But there are two possibilities. And so maybe I shouldn't have been so cavalier in picking only one of these things. Maybe the thing to do would be to actually give myself a bit more freedom, and let's just use some arbitrary combination of those two possibilities. So let's call this one E1 and this one E2. So I'm going to try instead x0 is equal to C1E1 plus C2E2, and lambda naught is still going to be A, which is 1. So I'm going to try that. So I'm going to give myself a bit more freedom by having some arbitrary constants in here and having some multiple of that. What happens if I do that? Okay, so instead of this, I'm going to have something slightly more general now. I'm going to have A minus AI times x1. It is equal to lambda 1 x0 plus bx0. I'm going to leave the x0 in there. That's what's in here. Okay, so what I can do is, well, I can come along and now I can multiply by that one. So I can, let's call this one E1 dagger, and this is E2 dagger. So I can do the product with E1 dagger and then the product with E2 dagger. I have two ways of doing it, so let's do both. So if I do it with that one, I end up with lambda 1 E1 dagger x0 plus E1 dagger b x0 is 0. And I can solve for lambda 1, but there's not much point in solving for lambda 1 at this point because hidden inside the x zeros are some c's. Okay, so let's not do that. Let's just introduce this into the equation at this point. So I get lambda 1, and then I get c1, and then I'm going to get some number which is e1 dagger e1. Now I'm also then going to get a lambda 1 c2 e1 dagger e2. So I've got that, and this I'm just going to throw onto the other side. I get an E1 dagger B E1 times C1, and a C2 E1 dagger B E2. Right, so this is the actual equation that I get from applying the Fredholm alternative on the first of these. And then there will be another one where I simply replace that by E2. So let's just write this as a J, just to emphasize the fact that there are two ways of doing it with J is equal to 1 or 2. All right, so I've retired from what we did before. I've made things a little bit more general in the hope that I'm going to be able to cure any difficulties, any ambiguities. And at this point, I suddenly realize that there's really two equations. I have a C1 and a C2, and I have a lambda 1. And then there's going to be a bunch of numbers in here as well. Well, let's just see what that is. If I think about it, I'm going to have a lambda 1, there's a C1 and a C2. So there's a lambda 1, there's a C1 times something, plus a lambda 1 C2 times something, equals a C1 times something plus a C2 times something. Right, those are numbers, and I've just picked out the things that I don't know, and there are two of these. Right, so this is a two set of equations, a couple of equations, and I've got to solve these for the lambda 1s and the c's, presumably. Well, if I think about that, I realize all of a sudden that I've just arrived at another eigenvalue problem. All right, this is actually another eigenvalue problem. I can think about this is lambda times a vector equals a matrix times a vector. And I've got two of these equations, so if I was to reconstruct this as a matrix problem, I would exactly get a 2 by 2 matrix problem. So by putting the C1 and the C2 in here, and going through all of this, applying both solvability conditions, I get a 2 by 2 matrix problem. So I had a multiplicity of 2, I've got a new 2 by 2 matrix problem. So this is what generally happens when you have repeated eigenvalues, but you have a full complement of eigenvectors. You actually end up with another eigenvalue problem, and the order of it, it's an n by n, where n is the multiplicity of the eigenvalue. So that's how it works formally. Let's do it specifically in this example. It'll be a bit more transparent when we go through it like that. So this is the more general thing. Now let's go through the details. Okay, so I have that and that here and here. Okay, so let's just have a quick look at B x naught. That's going to be C1, and B was 1, 1, 0, 1, 1, 0, 1, 1, 1. And this is E1. So this is 1, 1, 1. That times that. And then I get a C2 from here. That's going to be 1, 1, 1 again. So that's Bx naught. So what have I got? I've got, in this equation, I have A minus AI times x1 equals lambda 1, and it's C1 100 plus C2, 0, 1, 0. So that's that one. That's the first term here. And then we've got Bx naught, that's this one. So that's C1, 1, 1, 1, plus C2, 1, 1, 1. So that's the equation. Now I know that if I now come along and multiply by that one or that one, I get rid of the left-hand side. So what does that give me? So let's use the first one. So I get on the right-hand side, lambda 1, C1, and then this one times that one, that's just 1. Then I've got plus lambda 1, C2, that times that gives me 0. Then I've got this one, that gives us C1, and the dot product of that one and that one is 0, and the product of that one and that one is also 0, so that's all I get once I take this vector and multiply that equation. A lot of these things just disappear. Now let's do it with that one. I get 0 equals, okay, so multiplying by that one, I get 0. Coming along here, I get lambda 1, C2, and that times that is 1. Now this times that is 1, and this times that is 1. Okay, so that's the new system of equations that I've just arrived at by applying both solvability conditions at once. Okay. What does this now tell me? Well, I can now solve this for what I need to solve it for. But before I do that, let's just write it as a matrix problem. So I have lambda 1, C1, C2. That's this term and this term. Those I'll put on the other side of the equation. And so I'm going to have 0, 0 for the matrix that I'm going to have to put in, because there's nothing there. And then I put minus 1 there to get the C1 plus C2. So this is the matrix problem that's equivalent to that. And you see exactly how it's now this eigenvalue problem for a new eigenvalue, which is lambda 1. That's the eigenvalue correction. And the eigenvector is C1, C2. And I could solve it as another eigenvalue problem, but this exercise was simply to show how you're getting this new eigenvalue problem, this new 2 by 2 eigenvalue problem, because we've got a multiple eigenvalue with multiplicity 2 with a full complement of eigenvectors. However, it's obviously a lot easier to practically solve the problem just to go back to here. So I can either put C1 is equal to 0 to solve this one, and if C1 is equal to 0, that tells me that lambda 1 plus 1 times C2 needs to be 0. So that's one way of solving this set of equations. So I can choose C2 is equal to 1, say, and lambda 1 has to be minus 1. So this and this, that's one way of solving it. Right? That's one of the possible solutions. And then the other one is to say, okay, well, lambda 1 is 0. And if lambda 1 is 0, then C1 is equal to C2. So I could put C1 is equal to 1, and C2 is minus 1. Right, so that's the solution of this new eigenvalue problem. And so let's just recap what we're going to have. It's kind of interesting the way it worked out now. So instead of solving the leading order problem and getting an answer, we had some ambiguity in the leading order solution. What we actually now find is that x0 is equal to either, well, I have this one, let's imagine we're doing this case. So that was to say that C1 was 0 and C2 is 1. So that means we had the E2. That's what x0 was. Lambda 1 was equal to A, which was equal to 1, and lambda 0 rather, and lambda 1, the correction is equal to minus 1. Right? So this is actually what you should have taken as the eigenvector, and that's how you perturb it. That corresponds to the top choice there. The other case would have been to say, okay, well, my leading order eigenvector was x0 equals 2, so C1 and C2 are equal and opposite. C1 is 1 as a choice. So this is 1, 0, 0, minus 0, 1, 0. That's what x0 ought to have been. Lambda 0 is still 1. And the correction, in this case, is 0. Right, so in other words, I don't perturb the eigenvalue here at order epsilon. There may well be a correction of order epsilon squared, but I don't get any correction of that order for this particular leading order eigenvector. This one does have one. This one says that lambda is 1 minus epsilon, and so on. This one says lambda is equal to 1 plus 0 times epsilon, and so on. Okay, so that's the way that you deal with multiple eigenvalues when you've got all of these eigenvectors lying around to help you out. The issue is that there's so many of them that there's so many solvability conditions that you must take that you have to adjust what your leading order solution is, build in enough freedom to solve it at next order, and you end up with a new eigenvalue problem by doing that. So this is this sort of simple case. This is the end of the segment. We'll now go on and do the third segment, which is the degenerate case next.